So what is drag, also known as air resistance? Well, it's a force that, like friction, opposes the direction of an object's motion. So if you're moving through a fluid, such as air or water, in some direction, so here's our velocity, then the force of drag is going to resist that motion and point in the opposite direction. Right, so as the ball here that I've drawn has a velocity that changes, then the direction of the drag force is also going to change to point in the opposite direction. Now, on top of that, drag, unlike friction, depends on how fast you're going. Right, so you can experience this if you're driving in a car or just running or riding a bike. Right, the faster you go, the more that you feel the force of the air on you. So if you stick your hand out of a car window at 30 miles an hour, you feel a certain amount of force. But if you're going 60 miles an hour, you feel a lot more force. And it's also going to depend on something about the fluid that you're moving through. Right, so you feel a lot more drag going through water. If you ever try and stand in a pool and run through the pool, it's a lot harder than running in the air. And then finally, it also depends on the size of the object. So, if again you have your hand sideways, you're going to feel a lot more force than if you turn your hand so that you're facing this way, presenting a lot less area. So let's see if we can figure out an expression for the drag force. Well, so like I said, it's going to depend on what kind of fluid you're moving through, and as it turns out, it depends on the density of that fluid, which we call rho. So rho is the fluid density. And it depends on the area that is moving in that direction. Now it turns out that the important area is the cross-sectional area, right? So my hand has the same area no matter how I do it, but it's the cross-section. Here I have a much bigger cross-section moving in the direction as opposed to when I go here, right? So fluid density, area, the cross-sectional area. And then it also needs to depend on the object's velocity somehow. Right, so rho times the area times the velocity. Now, can that be an expression? Well, one thing that we do to try and check this is to check the units. So if I say, here, let's look at the units. Well, density has units of kilograms per cubic meter. Area has units of meters squared, and then velocity has units of meters per second. But what units do we need to have? Well, a force has units of newtons, which is kilogram meters per second squared. Right, because it's a mass times an acceleration. So do we have the right units here? Well, we can see that I've got the kilograms right, but I only have one factor of seconds in the bottom. And then I can see I have 3 factors of meters in the top and 3 factors on the bottom, so those would all cancel. So this can't work as an expression for the drag force on an object. What I need then is 1 more meter on top and 1 more seconds in the bottom. Well, I can get that by squaring the velocity. So if I square the velocity, then here I get meters squared, I get seconds squared. So now if I look at the units, this meters cubed cancels out with 3 of the meters up there. And now I have the right units. So this gives me a good idea of what the drag force on an object could be. Now it turns out that the way that this is actually written down we get a little bit more complicated than that. So it turns out that the way it's normally written is there's a factor of 1/2. And then there's also this coefficient c. And c tells us about the shape of the object. So as you may be familiar with, certain shapes are more aerodynamic than others. So even if you have a cube with the same cross-sectional area as a sphere, they're going to have slightly different drag forces. So that's something that you can look up, and in this programming exercise, we're going to be looking at spheres all the time. So that's a number that won't change. So this all together gives us the drag force on an object.